Let me ask you a strange question. Right now, as you sit there watching this, what exactly is holding you to the earth? Most people answer instantly. Gravity. It sounds simple, obvious, almost boring. An invisible force pulling everything downward. Apples fall, rain falls, you fall, case closed. But here is the disturbing part. According to physics, that explanation is not really true. In fact, the deeper scientists looked at gravity, the stranger it became. And this is exactly the kind of mystery that fascinated Richard Feynman. Feynman loved simple questions that secretly hide enormous mysteries. And gravity is one of the biggest, because the more carefully you look at it, the less it behaves like a force at all. Let's start with something ordinary. Drop a pen, it falls. We say gravity pulls it down. But here is the strange thing. If gravity were just a normal force, like pushing a box or pulling a rope, then falling objects would behave very differently. Imagine dropping two objects, a heavy rock and a light feather. At first, it seems obvious that the heavier object should fall faster. After all, gravity should pull harder on heavier things. But when scientists actually tested this carefully, something shocking appeared. In a vacuum where air resistance is removed, everything falls at exactly the same speed. A hammer, a feather, a bowling ball, a grain of sand, they all accelerate toward Earth in exactly the same way. That is incredibly strange, because if gravity were simply a pulling force, heavier objects should behave differently. But they don't, and this puzzled scientists for centuries, until a completely radical idea appeared. What if gravity is not a force at all? What if something else entirely is happening? Imagine you are inside an elevator. Suddenly the cable snaps. The elevator begins falling. Inside, something bizarre happens. You start floating. Your keys float beside you. Your coffee floats in the air. Inside that falling elevator, gravity seems to disappear. But nothing about Earth has changed. Earth is still there. Gravity is still there. Yet you feel weightless. This strange observation led to one of the most revolutionary insights in physics. Objects are not actually being pulled down by gravity. Instead, they are simply following the natural paths through space and time. This idea became central to the work of Albert Einstein. Einstein realized that gravity is not a force in the traditional sense. Instead, massive objects like planets and stars warp the very geometry of space and time. Imagine stretching a rubber sheet. Now place a heavy bowling ball in the center. The sheet bends. If you roll a marble across the sheet, it curves toward the bowling ball, not because the ball is pulling it, but because the surface itself is curved. This is roughly how gravity works. Earth bends the fabric of space, time around it, and objects simply follow the curved paths created by that distortion. They are not being pulled. They are moving along the straightest possible path in a curved universe. And that idea changes everything. Suddenly, gravity is no longer a mysterious pulling force. It is geometry, the shape of reality itself. But the mystery goes even deeper. Because physicists still don't fully understand gravity, gravity behaves very differently from the other fundamental forces of nature. Electromagnetism can be explained through quantum particles. The strong nuclear force has particles. The weak nuclear force has particles. But gravity. We still have no confirmed quantum particle for gravity. Physicists suspect one might exist. They call it the graviton. But no experiment has ever detected one, which means gravity remains one of the biggest unsolved puzzles in physics. And this is something Richard Feynman openly admitted. Feynman once explained that gravity is one of those phenomena that appears simple yet hides profound mystery. You drop an apple, it falls. Simple. But why it falls and what gravity truly is, that question remains partly unanswered. Even our most advanced theories may only be approximations, because when scientists try to combine gravity with quantum mechanics, the mathematics begins to break. Black holes create paradoxes. The beginning of the universe becomes mysterious. Space and time themselves may not even be fundamental. Some physicists suspect gravity could emerge from deeper laws of information. Others believe space, time itself, might be a kind of cosmic illusion, meaning the thing we call gravity could be something even stranger than curvature, something we have not yet fully discovered. So the next time you drop a pen, pause for a moment. What you are seeing is not just an object falling. You are watching the geometry of the universe guiding motion through curved space-time. You are witnessing the quiet influence of an invisible structure that shapes galaxies, bends light, and holds entire solar systems together. Gravity looks simple, but beneath that simplicity lies one of the deepest mysteries in science, and perhaps the most beautiful lesson physics offers. The universe is far stranger than our everyday intuition. And the more carefully we look, but the story of gravity becomes even stranger. Because once scientists realized that gravity is not really a force, a deeper question appeared. If gravity is not pulling objects down, then why do we feel weight? Think about this carefully. Right now, you are sitting in a chair. You feel your weight pressing against it. It feels as if the earth is pulling you downward. But according to modern physics, something very different is happening. You are not being pulled down. Instead, the ground is pushing you up. This sounds completely backwards, but it becomes clearer if we imagine something unusual. Imagine you are floating in deep space, far away from planets and stars. You feel weightless. Now imagine a spaceship begins accelerating upward. Suddenly you feel pressed against the floor. Your body becomes heavy. You feel weight, but there is no gravity in deep space. The only thing happening is acceleration. This simple thought experiment led to one of the most powerful ideas in physics, the equivalence principle, discovered by Albert Einstein. Einstein realized something shocking. Gravity and acceleration are fundamentally indistinguishable. If you are inside a sealed room, there is no experiment you can perform that will tell you whether you are standing on Earth or accelerating upward in space. The physics is identical. And this observation changed everything because it suggested that gravity is not a traditional force. Instead, it is the result of curved space, time guiding motion. Imagine space not as empty nothingness, but as a flexible structure, a fabric that can bend, stretch, and warp. Massive objects distort this structure. Planets bend it. Stars bend it. Black holes bend it dramatically. Objects moving through this warped geometry simply follow the natural paths available to them. They are not pulled. They are guided. Think of an airplane flying across the surface of Earth. The pilot may feel like they are traveling in a straight line, but from space we see that the plane is actually following a curved path along Earth's spherical surface. In the same way, objects moving through space, time follow curved paths created by gravity. And here is where things become even more fascinating. Gravity does not just affect objects. It affects time itself. Time slows down near massive objects. This is not science fiction. It is a measurable fact. Clocks near Earth tick slightly slower than clocks far away in space. The difference is tiny, but modern technology can measure it precisely. Even the GPS satellites orbiting Earth must account for this effect. If scientists ignored gravity's influence on time, GPS navigation would become inaccurate within minutes. This phenomenon is called gravitational time dilation, and it means that gravity is not just bending space. It is bending time, which leads to an astonishing conclusion. The universe is not simply 3 dimensions of space. It is a 4-dimensional structure called space-time, and gravity is the curvature of that structure. But despite the elegance of this theory, a massive mystery remains, because our 2 greatest theories of physics do not agree with each other. On one side, we have general relativity, Einstein's theory explaining gravity. On the other side, we have quantum mechanics, the theory describing the microscopic world of atoms and particles. Both theories work incredibly well. Each predicts experimental results with astonishing accuracy. But when scientists try to combine them, the equations collapse into nonsense. Gravity refuses to behave like the other forces. And this deeply puzzled physicists like Richard Feynman. Feynman once explained that understanding gravity at the quantum level might require a completely new way of thinking about reality, because space, time itself, might not be fundamental. Some theories suggest that space and time emerge from deeper structures. Others propose that the universe behaves like a vast network of information. In these models, gravity may not be a fundamental force at all. Instead, it could be something that emerges from the collective behavior of the universe, like temperature emerging from the motion of atoms, or waves emerging from the motion of water molecules. And if that idea is true, then gravity might not actually exist in the way we imagine. It could be a large-scale illusion created by deeper physical laws. This possibility excites physicists because it suggests something extraordinary. Our current understanding of reality might only be a rough approximation, just as Newton's gravity was replaced by Einstein's theory. Einstein's theory may eventually be replaced by something even deeper, a theory that explains why space-time exists, why gravity emerges, and how the universe truly works at its most fundamental level. So when you watch an apple fall from a tree, you are not simply seeing gravity. You are witnessing the shape of the universe guiding motion. You are seeing space and time themselves directing the paths of objects. And beneath that simple everyday event, there may be layers of physics we have not yet discovered. Because the universe rarely reveals its secrets easily. It hides them inside ordinary experiences. A falling apple, a bending beam of light, a clock ticking slightly slower near Earth. These small clues hint at something enormous. Reality is not as simple as it appears, and gravity, one of the most familiar phenomena in our lives, may also be one of the deepest mysteries in the cosmos. And the closer we look, but the mystery of gravity does not end with curved space and time. In fact, that is only the beginning, because once physicists understood that massive objects bend space, time, a new question appeared. If gravity is the curvature of space and time, then how fast does that curvature change? In other words, if something massive suddenly moves, does gravity react instantly across the universe? For a long time, scientists believed it might. Even Isaac Newton assumed gravity acted instantly at any distance. If the sun moved, Earth would immediately feel the change. But this idea always bothered scientists, because instantaneous effects would violate one of the most important rules in physics. Nothing in the universe can travel faster than light. Not information, not energy, not even gravity. This became clear after the work of Albert Einstein. Einstein realized that changes in gravity must also travel at a limited speed, and that speed is the same as light. This means something astonishing. Gravity moves through the universe as waves, ripples in the fabric of space-time. Imagine throwing a stone into a calm lake. Waves spread outward across the water. Now imagine two massive black holes colliding in deep space. The collision sends ripples through space, time itself. These ripples travel across the universe at the speed of light. For decades, this idea sounded almost impossible to test. The waves would be unimaginably tiny, so small that detecting them seemed hopeless. Yet physicists kept trying. Then in 2015, something extraordinary happened. Scientists using the LIGO observatory detected the first gravitational waves ever observed. The signal came from two merging black holes over 1 billion light years away. When the waves reached Earth, they stretched and squeezed space itself by less than the width of a proton. And yet the detectors measured it. For the first time in human history, we directly observed ripples in space-time, a prediction of Einstein's theory confirmed 100 years later. But discoveries like this only deepen the mystery. Because the more we learn about gravity, the less we seem to understand its true nature. Take black holes, for example. Black holes are regions where gravity becomes so strong that not even light can escape. At their center lies something called a singularity, a point where space and time appear to break down completely. The laws of physics stop making sense. Equations explode to infinity. This is deeply troubling for scientists, because a true theory of nature should never produce infinities like that. It suggests our understanding is incomplete, and physicists like Richard Feynman often emphasize this point. When equations break down, it usually means we are missing something fundamental. Black holes may be telling us that our picture of gravity is still unfinished. Another mystery appears when we look at the universe itself. According to our observations, gravity should slowly pull everything together. Galaxies should eventually collapse inward. The universe should gradually shrink, but that is not what we see. Instead, the universe is expanding, and not just expanding. It is accelerating. Galaxies are flying away from each other faster and faster. Something is pushing the universe apart. Physicists call this mysterious influence dark energy, and its existence raises one of the biggest puzzles in modern science, because dark energy seems to work against gravity, while gravity pulls things together. Dark energy pushes space apart. No one fully understands what dark energy is, and it may represent an entirely new form of physics. Meanwhile, there is another strange puzzle known as dark matter. When astronomers observe galaxies, they find that stars move far too fast. According to gravity alone, galaxies should fly apart, yet they remain intact. Something invisible must be providing additional gravitational pull. Scientists call this missing mass dark matter. We cannot see it. We cannot directly detect it. Yet it appears to make up most of the matter in the universe. This means something astonishing. Everything we can see, stars, planets, galaxies, even our own bodies, represents only a tiny fraction of the universe. Most of reality is invisible, and gravity is one of the few tools we have for detecting it. But even here, the story grows stranger. Some physicists believe dark matter may not exist at all. Instead, they argue that gravity itself may behave differently at enormous cosmic scales. If this is true, it would mean our understanding of gravity is still incomplete. And this possibility excited thinkers like Richard Feynman, because Feynman often reminded students that science is never finished. Every theory is provisional. Every explanation is temporary. Nature always has deeper layers waiting to be discovered, and gravity may be hiding some of the deepest secrets of all. The force or geometry that shapes galaxies, the phenomenon that controls black holes, the mysterious influence that governs the expansion of the universe. Gravity appears simple, but beneath that simplicity lies a cosmic puzzle stretching across billions of light years. And perhaps the most fascinating part is this. Every time we think we understand gravity, the universe reveals something new, something stranger, something that reminds us how little we truly know, which means the falling apple that once inspired Isaac Newton may still be teaching us lessons today, because the mystery of gravity is far from solved. And yet, even after centuries of discovery, gravity still refuses to fully reveal its secrets. Think about that for a moment. Humanity has discovered electricity. We have mapped the atoms inside matter. We have built machines that split nuclei and machines that explore other planets. And yet the phenomenon that keeps your feet on the ground remains partly mysterious. Gravity is everywhere. It shapes galaxies. It guides planets. It controls the motion of stars. But when physicists try to describe exactly what gravity is at the deepest level, the answer becomes uncertain. Even brilliant minds like Richard Feynman admitted something remarkable. We can calculate gravity with incredible precision. But explaining what it truly is another matter entirely. This strange situation appears again and again in physics. We learn how something behaves, but the deeper why often remains hidden, and gravity may be the most dramatic example of this. To understand why, imagine shrinking yourself down to the smallest scales of reality, atoms. Inside atoms are electrons. Inside atomic nuclei are protons and neutrons. Inside those are quarks. And beyond that, physics becomes uncertain. At these tiny scales, the universe behaves according to the strange rules of quantum mechanics. Particles do not have definite positions. They behave like waves. They appear and disappear in a haze of probabilities. This microscopic world is wildly different from the smooth universe described by gravity. Gravity treats space-time like a continuous fabric. Quantum mechanics treats reality like a storm of fluctuating particles. And when physicists try to combine these two pictures, something strange happens. The mathematics breaks. The equations produce impossible infinities. Theories collapse. Gravity simply refuses to behave like the other forces. Electromagnetism can be explained with particles called photons. The strong nuclear force has gluons. The weak nuclear force has W and Z bosons. But gravity, if gravity has a particle, it would be called the graviton, a tiny quantum carrier of gravitational interaction. Yet no experiment has ever detected one. And detecting it may be incredibly difficult, because gravity is unbelievably weak compared to other forces. Consider this. Right now, the entire mass of the Earth is pulling you downward. Yet a tiny refrigerator magnet can easily lift a paperclip against the pull of the entire planet. That means electromagnetism is vastly stronger than gravity. Gravity dominates the universe only because it always adds up. Electric charges cancel each other. Positive and negative balance out. But mass does not cancel. Mass only accumulates, which is why gravity becomes powerful on astronomical scales. Planets, galaxies, black holes. But on the quantum level, gravity is almost invisible. This enormous difference between scales makes gravity uniquely difficult to study, and it has led physicists toward bold new ideas. One possibility is that gravity might not actually be a fundamental force. Instead, it could emerge from deeper microscopic processes. This idea is similar to something we experience every day: temperature. Temperature feels like a fundamental property of matter, but it is not. Temperature emerges from the motion of countless atoms. If you zoom in close enough, temperature disappears. All that remains are particles moving and colliding. Some physicists believe gravity may work in a similar way. Space-time itself might emerge from deeper structures. Gravity might be the large-scale effect of microscopic information. In this view, the universe might behave more like a giant computational system than a simple mechanical machine. Some theories even suggest that space-time is woven from quantum information itself, that the geometry of reality arises from patterns of entanglement between particles. If this is true, gravity may be a kind of statistical effect, a large-scale illusion created by deeper quantum processes. This radical idea excites physicists because it could solve several mysteries at once. It might explain why gravity behaves differently from the other forces. It might explain black hole paradoxes. And it might reveal what happened at the beginning of the universe. Because gravity becomes especially strange when we look at the origin of everything. According to our best observations, the universe began about 8 billion years ago, an event we call the Big Bang. At that moment, the universe was incredibly hot and dense. All matter and energy were compressed into an extremely small region. But when physicists try to calculate the conditions at that moment, gravity becomes infinite. Space-time curvature becomes infinite. Temperature becomes infinite. Once again, the equations collapse. This tells us something important. Our theories cannot yet describe the true beginning of the universe. We need a deeper understanding of gravity, and that is exactly what physicists are searching for today. Several major ideas compete to explain gravity at the quantum level. One is string theory. In string theory, The fundamental building blocks of reality are not particles, but tiny vibrating strings. Different vibrations create different particles. One of those vibrations naturally behaves like a graviton. Another idea is loop quantum gravity. This theory suggests that space, time itself, may be made of tiny discrete units, like pixels in a digital image. Instead of a smooth fabric, space might actually be a granular structure. At incredibly small scales, space and time could behave more like a network than a continuum. Both of these theories attempt to unify gravity with quantum mechanics. But so far, neither has been experimentally confirmed, which means the mystery continues. And perhaps the most fascinating part is this. The deeper we investigate gravity, the more it seems connected to everything else. Black holes, quantum information, the structure of space-time, the expansion of the universe. Some physicists suspect gravity may hold the key to a final unified theory of nature, a theory explaining all forces and particles within a single framework, a dream sometimes called the theory of everything. And yet, despite all these grand ambitions, gravity still appears to us in the simplest way possible. You drop an apple, it falls, just as it did centuries ago when Isaac Newton watched one fall from a tree. Newton discovered the mathematical rules governing gravity. Later, Albert Einstein revealed the deeper geometric explanation. And physicists like Richard Feynman continued pushing the boundaries of understanding. Yet even now, the full story remains unfinished. Gravity remains one of the greatest unsolved puzzles in science. But perhaps that is exactly what makes it so beautiful, because every mystery in physics reminds us of something profound. The universe is far more complex and subtle than our everyday intuition suggests. What looks simple on the surface often hides extraordinary depth. A falling apple, a bending beam of light, a ripple of gravitational waves crossing billions of light years. These events reveal something remarkable. Reality is not just a collection of objects moving through empty space. It is a dynamic structure, a geometry, a network of relationships between matter, energy, space, and time. Gravity is the language through which that structure reveals itself. And every discovery about gravity brings us one step closer to understanding the deeper architecture of the cosmos. But perhaps the most important lesson is this. Science is not a collection of final answers. It is an ongoing journey of curiosity. Each generation of scientists sees further than the last because they stand on the shoulders of those who came before. Newton, Einstein, Feynman, and countless others. Each one uncovered part of the puzzle, yet none of them claimed the mystery was finished, because the universe always has more to teach us. And gravity, the force, or perhaps the geometry that shapes the cosmos, may still hold secrets that will redefine our understanding of reality. So the next time you see something fall, remember this. You are not simply watching an object drop. You are witnessing the quiet curvature of space, time, the invisible architecture of the universe guiding motion through cosmic geometry, a phenomenon so familiar, yet so mysterious, that even the greatest physicists in history never stopped wondering about it. And perhaps that curiosity itself is the most powerful force of all, because it keeps us searching, keeps us questioning, and keeps us exploring the strange and beautiful universe we inhabit. Now here is where the mystery of gravity becomes truly philosophical, because when physicists examine gravity closely enough, they begin to ask a question that almost sounds absurd. What if gravity is not really a force, and not even truly a curvature of space-time? What if gravity is something deeper still? To understand why scientists ask such strange questions, we need to look at one of the most mysterious objects in the universe, black holes. Black holes are the ultimate laboratories of gravity. They are places where gravity becomes so strong that it reshapes the structure of space and time in extreme ways. Near a black hole, time slows down dramatically, light bends sharply, and space itself is stretched toward the center. According to Albert Einstein's theory of general relativity, a black hole forms when a massive star collapses under its own gravity. As the star collapses, gravity becomes stronger and stronger. Eventually, the escape velocity becomes greater than the speed of light. And once that happens, nothing can escape. Not light, not matter, not information. At least, that was the original idea. But in the 1970s, something astonishing happened. A physicist named Stephen Hawking made a discovery that shocked the scientific world. Using quantum mechanics, Hawking realized that black holes are not completely black. They slowly emit radiation. This phenomenon became known as Hawking radiation, and it means something incredible. Black holes can slowly evaporate. Over immense periods of time, they lose energy and eventually disappear. At first glance, this might not seem too strange, but it creates a massive problem for physics because of something called the information paradox. In quantum mechanics, information about physical systems can never be destroyed. The universe may scramble information, it may spread it out, but it cannot erase it completely. Yet, if a black hole evaporates completely, all the information about everything that fell into it would seem to vanish forever. That would violate the fundamental laws of quantum physics, which means one of our theories must be incomplete. Either our understanding of gravity is wrong, or our understanding of quantum mechanics is wrong. And physicists have been wrestling with this puzzle for decades. Interestingly, thinkers like Richard Feynman always encouraged scientists to embrace such paradoxes, because paradoxes are often where new discoveries are born. They signal that something fundamental is missing. And in the case of gravity, many scientists suspect that the missing piece may involve information. This idea leads to one of the most surprising proposals in modern physics, the holographic principle. According to this concept, our universe might behave like a hologram. In a hologram, a two-dimensional surface can encode information about a three-dimensional image. Similarly, some physicists believe the information describing a region of space might actually exist on its boundary. This idea first appeared when scientists studied black holes. They noticed that the information inside a black hole seems to scale with the area of its event horizon, not with its volume. That is incredibly strange. It suggests that the three-dimensional interior of a black hole might actually be encoded on its two-dimensional surface. And if that principle applies to black holes, it might apply to the entire universe, which leads to an astonishing possibility. The universe we experience in 3 dimensions might be a projection of information stored on a distant cosmic boundary. In such a picture, gravity could emerge from the way information is organized. This radical perspective has inspired several new theories. One of them suggests that gravity may arise from entropy. Entropy measures the amount of disorder in a system. According to this idea, gravity could be an emergent force created by the tendency of systems to maximize entropy. Objects move toward massive bodies because doing so increases the number of possible microscopic configurations. In other words, gravity might not be fundamental at all. It might simply be the statistical behavior of information in the universe. This idea is still speculative, but it highlights how mysterious gravity remains, and it shows how physics is slowly transforming our understanding of reality. For centuries, we believed the universe was built from particles moving through empty space. But modern physics suggests something far stranger. Space may not be empty. Space may be a dynamic structure filled with quantum activity. Particles may not be fundamental. They may emerge from deeper fields. And gravity may not be a traditional force. It may emerge from information, entropy, or quantum geometry. Each layer of understanding reveals deeper complexity. And yet, despite all this complexity, gravity continues to operate with elegant simplicity across the cosmos. It forms stars. It sculpts galaxies. It orchestrates the motion of planets. Without gravity, the universe would look completely different. Matter would never gather into stars. Galaxies would never form. Planets would never exist. And life as we know it would be impossible. Gravity is the cosmic architect, the quiet force or structure that shapes the large-scale universe. But perhaps the most fascinating aspect of gravity is how it connects the smallest scales to the largest. On one hand, gravity governs the motion of galaxies billions of light years apart. On the other hand, it may arise from microscopic quantum processes occurring at unimaginably tiny scales. That means gravity may bridge two extremes of reality, the cosmic and the quantum. Solving the mystery of gravity might therefore reveal the deepest structure of the universe, a unified framework explaining space, time, matter, energy, and information. And if that happens, it may transform our understanding of existence itself. Because gravity is not just a scientific problem. It is a window into the architecture of reality. It tells us that the universe is not static. It is dynamic, flexible, evolving. Space bends. Time stretches. Information flows. And within this vast cosmic system, gravity quietly shapes everything we observe. But perhaps the most important lesson gravity teaches us is humility. Every time scientists believed they fully understood gravity, new discoveries revealed deeper mysteries. Newton believed gravity was a universal force. Einstein showed it was curvature in space-time. Modern physics suggests it may emerge from quantum information. Each explanation brings us closer to truth, yet each also reveals new questions. And that is the beauty of science. It is not about final answers. It is about an ever-deepening understanding of nature. The universe is not obligated to be simple. It is not obligated to match our intuition. Instead, it invites us to explore its mysteries with curiosity and imagination. And gravity, one of the most familiar phenomena in our lives, remains one of the greatest mysteries of all. So the next time you see something fall, pause for a moment. That simple motion connects you to the deepest questions in physics. Why does space bend? Why does time slow near massive objects? How does gravity emerge from quantum reality? And what hidden structure of the universe lies beneath it all? These questions continue to drive physicists forward. And perhaps someday, someone will finally uncover the deeper truth behind gravity, a discovery that may change our understanding of the cosmos forever. Until then, the mystery continues, and gravity remains one of the most beautiful puzzles the universe has ever offered humanity.